All right, so let's jump in and take a look at the first worksheets for today. This is 8.3 lecture worksheets. And one thing I mentioned is that after the midterm, we have less math, and that is largely true. There's numbers still. And you will see, even though there are numbers in pH, so pH values are numbers, and even though I mentioned this about the logarithmic scale or the powers of 10, what we're going to be working with for pH and the concentrations are whole number values, and you really actually don't need a calculator for even this, even though these are logarithmic. You can calculate logarithms using a calculator, but we actually don't need to do that for the scope of what we're doing in Chem 9. So you will see numbers, but you can do all of these calculations without a calculator. So these are the idea of pH is it will tell you quickly, the pH value will tell you quickly if a solution is an acid or a base, an acidic solution or a basic solution. And so this is pH less than 7 are your acids. Those are called acidic solutions. pH greater than 7, these are your solutions that are bases or basic solutions. Okay, and basic solutions are also called alkaline. If you've ever heard of alkaline thing, which we'll talk about in lab in 2 weeks, alkaline water means that it is a basic solution that has a pH greater than 7. And that's because you also have one more type of solution, which is called a neutral solution. And that's a solution where the pH is exactly equal to 7. Now, the neutral solution, the only natural neutral solution is water. So water is a neutral solution naturally. You can have solutions that are also pH 7 that are not naturally pH 7, but they can be adjusted to have the pH of 7. Or you can have solutions that have no hydrogen or hydroxide and are pH 7 because they are just ionic compounds. So water, though, with hydrogen and hydroxide is a pH of 7 naturally because there's an equal concentration of hydrogen to hydroxide. So the pH values are important because they quickly tell us what type of solution it is. And here is how pH is calculated in a simple manner. When you have the pH value as a whole number value, so not a decimal value, but when the pH is a whole number value, that pH becomes an exponent as the power of 10. And that number, that power of 10, describes the concentration of hydrogen. pH actually means the power of hydrogen. The pH stands for power of hydrogen. And what that is, it's a power of 10, that it is equal to the concentration of hydrogen ions. So 10 to the x is the concentration, or 10 to the minus x, I should put, that's a negative exponent, is the concentration of hydrogen ions. Okay, and so this pH value is going to be become a power of 10, and that's a negative value. It doesn't mean it is a negative value as far as a number value. It means that it is a negative power of 10, which is a fractional. So remember that 10 to the minus 1 means that there is a decimal in front of the ones place, or 10 to the minus 2, that there are 2 decimal places. There are 2 spots in front of the ones place. So that is not a negative value. Those are fractional values when you have a negative pH. Okay. And so this is the hydrogen when you have the pH value, that whole number value, like pH 6 in these examples down here, a pH 6 means that that pH 6 goes into here and it represents 10 to the minus 6, the concentration of the hydrogen ions. And that concentration is in molarity. That's that uppercase M. We've seen molarity before. Molarity is one of the units that are possible for concentrations. So the concentration units we talked about last time, the concentration units that we work with are parts per million, parts per billion, percent, and M, which is called molarity. Okay, so molarity, that uppercase M. And so when you have the power of 10, that is the concentration of the hydrogen ions in the units of molarity. So when you have the hydrogen ion concentration, you can calculate the hydroxide. So remember, this is called hydroxide, the OH. And the hydroxide is calculated also with a very simple equation. Let me actually circle this. This is a simple equation when you have the pH as the whole number value. This is another simple equation. You don't need to memorize it. You just need to know how to use it. But that this also is worked with when you have the pH value as a whole number value. You have a power of 10 for hydrogen, and you also can figure out the power of 10 concentration for hydroxide. And so that's because those powers of 10, when you multiply powers of 10, so that's what these brackets are, multiplying these powers of 10. When you are multiplying those powers of 10, which are exponents, you add them. Okay, so basically the concentrations are those powers of 10. They need to add up to -14. So we'll see this in here. When you have this pH of 6, you can quickly figure out the hydrogen ion concentration is 10 to the -6. Basically just put this 6 in here. And then the this equation where you have hydrogen times the hydroxide, those exponents need to add up to -14. So in order to get -14, the hydroxide has to be -8, or 10 to the -8 molarity is the concentration of the hydroxide. Okay, let's zoom in on this. So when you are given a constant, the pH value as a whole number value, so not a decimal value, but a whole number value like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1 through 14 is what we generally work with for pH. The pH value becomes a power of 10. I'm going to erase this to get this out of my way. Okay, so that pH value of 10 becomes a power of 10, or 10 to the -10, and I need to add the units molarity here. Okay, and that's the units of molarity are representing the concentration of hydrogen ion. So then, because this is a whole number value, we can still continue on and figure out the concentration of hydroxide ions, which need to add up to, that's what this second equation is, the concentration of hydrogen. You can figure out the concentration of hydroxide. It's going to be a power of 10, so that those powers of 10 add up to -14. So -10 plus -4 is how you can get to -14. And that's -4 and molarity, because it's still talking about a concentration. And so that's what those brackets, the brackets, those square brackets, indicate the concentration of whatever is in those brackets in the units of molarity. Okay, so let's see if we can figure out, when you are given the pH value, you can figure out the hydrogen. Or when you're given the hydrogen ion concentration, you can figure out the pH value. That's the first one. So when you have the hydrogen ion concentration of 10 to the -4 molarity, the pH value is 4. Not -4, because remember, not -4, just the number value without the negative sign. And so when you have the hydrogen ion, you can also figure out the hydroxide ion. So in order to get the hydroxide ion multiplied by the hydrogen ion, they both need to add up to -14. So that would be -10. And that is units of molarity for the hydroxide ion. To figure out the solution type, you use the pH to determine the solution type. And so remember, pH values less than 7 are acidic solutions. So that's what 4 is. That's less than 7. compared to exactly equal to 7 is neutral, or greater than 7 is basic. Okay, so let's look at this next one. When you have 10 to the minus 8 molarity is the hydrogen ion, you can figure out that the pH is that exponent, which is 8. Okay, and from the hydrogen ion, you can also figure out the hydroxide ion. So -8, you're going to need a -6 to get to -14. So those two added together. And the units of molarity. And then the solution type using the pH, a pH of 8 is greater than 7. So that's a basic solution. When you have, now you're given the pH of 7. So we can now move forward from the pH and calculate or determine without a calculator the hydrogen ion. So that's 10 to the minus 7 molarity. Okay. And remember, that doesn't mean it's a negative number. It just means that there are 7 zeros in front of the ones place. So this hydroxide also needs to be 10 to the minus 7, because those two -7s is how you get to -14 added up. And then looking at the pH, this pH of 7 is exactly equal to a neutral solution. Now, only when it is exactly equal to 7. So not 6.9, not 7.1, but only exactly equal to 7 is the definition of a neutral solution. So that's why most of the majority of solutions out there are either acidic or basic, because that's just statistically how many of them are going to be exactly equal to 7. Okay. So for the pH of 14, we can find the hydrogen ion. So that's 10 to the minus 14 molarity. And then the hydroxide. So 10 to the minus 14 leaves only 10 to the 0 molarity for those to add up to -14. And 10 to the 0 does not mean 0. Remember, 10 to the 0 is 1. 10 to the 0 is equal to 1. So that's okay. That means 1 molarity. The solution type, when it's 14, that is a basic solution. And what that means is that this 10 to the 0 or 1 molarity is a very high concentration of hydroxide ions. Remember, this is called hydroxide. It's a very high concentration of hydroxide ions. That's what a base is. It has a lot of hydroxides and a very low concentration of the hydrogen ions, these H+. Okay, let's take a look at the next one, which starts with 10 to the minus 3 molarity for the hydroxide. So working backwards from there, you can figure out the hydrogen ion concentration. So -3 means that this is going to be -11 molarity for the hydrogen ion, which means that this is a pH of 11. So the pH value of 11 is greater than 7, so that's a basic solution. Moving this up a little bit. This is the next one is 10 to the minus 5 molarity for the hydroxide. So working backwards from there, this is going to be the hydrogen is 10 to the minus 9. And then that means the pH is 9. pH of 9 is greater than 7, so that's a basic solution. Okay, so these are pretty straightforward, right? And you can do these without a calculator. But they are still number values to try to understand. And so this next graphic gets us to understanding these number values. So you have the acidic solutions that are less than 7. So that's everything less than 7 are your acids. Everything greater than 7 are your bases, and then exactly equal to 7 is neutral. So what you also have on here is what was shown on the video, the pH values. So this is increasing pH. So these are your low pH values, and these are your high pH values. And so this increases. So increasing pH, and you can see this increases by 1. So from 1 to 2 to 3 to 4 to 5 to 6, each step is 1. Okay. Now this compares to the hydrogen ion concentration, which I'm going to circle in red. The hydrogen ion concentration is a power of 10, and this is in the units of molarity, the uppercase M. And so what a pH of 1 is equal to is 10 to the minus 1 molarity. And this is the concentration of hydrogen ions, because remember, pH stands for power of hydrogen. It's a power of 10 of the hydrogen ion concentration. So this is 10 to the minus 1. So let's write that above that, is that pH of 1 is equal to 10 to the minus 1 molarity hydrogen ion concentration. So I'm putting hydrogen H plus and then in brackets, assuming you guys still remember that the brackets mean the concentration of whatever is in the brackets, which is hydrogen ion or H plus. Okay. And so that means that this is a 10 to the minus 1 is 0.1 molarity is the hydrogen ion. Okay. And so when you have this compared to the molarity 10 to the minus 1 compared to 10 to the minus 14, what's the difference between these? So 10 to the minus 1, is that high or low compared to 10 to the minus 14? So this is a high concentration or a high molarity compared to 10 to the minus 14. This is a low concentration or a low molarity. Why is 10 to the minus 14 a low molarity? Because there are 14 zeros in front of the ones place when you have 10 to the minus 14. Compared to 10 to the minus 1, there's only 1 0. Okay, so let's write that out there, is that this is a pH of, the pH of 14, writing it here, is the hydrogen ion concentration is equal to 10 to the minus 14 molarity. That's 14 zeros in front of the 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then a 1. That's a really small number compared to that. So that's why I wrote that this is a low molarity on this side, and that's a high molarity on that side. So even though this is increasing in pH going in this direction, what this is a decreasing hydrogen ion concentration. So decreasing H plus in brackets. Okay, and so that means that acidic solutions have hydrogen ion is the high, and they have the hydroxide ion concentration is low. Remember, those are related. And then basic solutions, bases have a low hydrogen ion and a high hydroxide. Okay, so they are related, is hydrogen ion and hydroxide ion, just as you saw with both of these in every solution, whether acidic, basic, or neutral, will have hydrogen ions and hydroxide ions. They are related. If one is high, the other is low. Okay, and so acids have a lot of hydrogen ion. Let's highlight that in green. Acids have hydrogen ion, but they still have some hydroxide. Bases have a lot of hydroxide, but they still have some hydrogen ions. Okay, so let's take a look now that we understand this graphic, what this means in terms of the number values for pH. So if you have a solution that's a pH 5, is it more acidic or less acidic? You got to circle one, compared to a solution of pH 6. So pH 5 compared to pH 6. You can see that increasing pH 5 to 6, this becomes more basic, and going in the opposite direction from 6 to 5 means that it is less acidic. Okay. Oh, sorry. No, sorry. I mean more acidic. Let me fix that. Okay. So the pH of 5 is less than 6, but you're going in the more acidic direction. So it's increasing pH, but it is becoming more of an acid. So sorry about that. I fixed myself. So it's more of an acid as you go lower in the pH. So pH 1 is the stronger acids, and then pH 2, 3, 4, 5, you're becoming less of an acid, more of a base. Okay. So pH 5 compared to pH 6, that's the next one. pH 5 compared to 6 is still going to be more acidic than pH 6. But now, what is going on with the hydrogen ions? the pH 5 solution compared to 6, does it have the comparison of hydrogen ions? It has either more or less hydrogen ions. So let's think about that. You can look at the pH 5 compared to pH 6. pH 5 is 10 to the minus 5 molarity hydrogen ions. pH 6 is 10 to the minus 6 molarity hydrogen ions. So remember what those negative exponent powers of 10 mean. It's how many places in front of the ones place, how many zeros. And so that means 10 to the minus 5 compared to 10 to the minus 6. That pH 5 has more hydrogen ions. Okay, and this has 10 times more. The difference of 10 to the minus 5 versus 10 to the minus 6 is a power of 10. Okay, so there's 10 times more in 10 to the 5, 10 to the negative 5 compared to 10 to the minus 6. Okay, let's talk about the pH 5 solution in the next one, but now compare it to a pH 7 solution. Okay, so pH 5 compared to pH 7. Let me erase this up here. When you have the pH 5 compared to pH 7, that's still going to be, in terms of being acidic, it's still going to be more acidic because 5 is lower than 7. It's closer to the low values, which are the strong acids. That's 1, 2. The smaller the number, the more of an acid. Okay, then does it have more or less of the hydrogen ions when you're talking about pH 5? This still has more hydrogen ions in the pH 5. And zooming in on this, this is pH 5, which is, move this out of the way, 10 to the minus 5 molarity compared to 10 to the minus 7 molarity. So 10 to the minus 5 compared to 10 to the minus 7. So 10 to the minus 5 has 0.5 zeros in front of the 1 compared to 7 zeros in front of the 1. Okay, and so this number is more, even though it's a small number, it's still a bigger number than this number. So that has 10 to the 2 or 100 times more hydrogen ions in the 10 to the minus 5 pH 5 solution. And then let's take a look at this one, which is comparing the solution of pH 5, this time to a solution of, let me erase this, the solution of pH 3. Okay, so going to compare it to pH 3, well, now that solution of pH 3 is lower than pH 5. And so that means that pH 5 solution is less acidic than the pH 3. Okay, so pH 3 is more acidic. Okay, and then the reverse of that is saying that pH 5 is less acidic. So that's why I circled less that time, because we're talking about acidic. Now let's see the comparison of hydrogen ions. So if your pH 5 is 10 to the minus 5 molarity versus the pH 3 is 10 to the minus 3 molarity. So does this, in terms of the hydrogen ions, the pH 5, does it have more or less hydrogen ions? So this pH 5, 10 to the minus 5 compared to 10 to the minus 3. 10 to the minus 5 is 5 zeros in front of the 1, compared to 10 to the minus 3 is 3 zeros in front of the 1. And so this is less, this number is less hydrogen ions in the pH 5 solution. It's less acidic, so there's less hydrogen ions. And then how many times less? Well, this step of 5 to 3 is 10 squared, or again, 100 times, but this time less of the hydrogen ions. And so going back up to this, you will see this graphic in other ways, not just the worksheet assignment, but also in Quizlet, that you have the increasing of pH, which is by 1. Well, the decreasing of hydrogen ions is a power of 10 with each 1. So this a power of 10, that's the difference between a logarithmic and a standard linear scale. Okay, let me move this up a little bit. All right, how do you guys feel about this?
Good.
Okay. I'll say it again. The ocean is basic. Solutions that are higher than pH 7 are basic solutions. Oceans all over the world are around pH 8.1, 8.2. So that's all the oceans. That they are basic. And even though 8 is close to 7, you know it's a power of 10. And so that is a whole power of 10 more basic than what would be a neutral solution. But in the moving in the decimal range from 8.2 down to 8.1, that is moving towards the acid range. So that's going down, which is becoming acidic. That's what acidification means, is that the pH is lowering. Very, very slightly, though, in the powers of 10 and, the decimal places of the powers of 10. So that means that yes, there's more hydrogen ion in the ocean. Yes, it's 8.1 instead of 8.2. But what the real consequences are really unseen. And that's why this problem is, I consider, bigger than climate change. But it is also similar to climate change in that climate change is increasing temperatures. But all the other effects of climate change, the storms, the hurricanes, the sea level rise, the droughts, we don't connect all those. Now you guys do because you're Chem 9 students, but your average person walking around, they don't connect all that. They'll just, turn up the AC one day. Well, here's the thing about ocean acidification. There's not a real understanding of this problem, in part because humans are not really affected by this. They don't live in the ocean, okay? But we will start seeing the effects of this in our food webs. And so I'm showing you this on the screen right now, is that what happens is the dissolving of shells. So coral reefs will dissolve, and those are habitats for fish that basically are fish that feed other fish and go on up in the food webs. And so that's also the shells of small things like shrimp, snails, lobsters. When their shells dissolve, that's basically like ripping someone's house out of, just taking the walls out of your house. What would you do if you suddenly have no house? So that's what happens to the marine life. So this is the consequences of the ocean acidification. It is because of atmospheric carbon dioxide. So right now, this is this slider bar down here. We have carbon dioxide at 300. And this is a pH here of about 8.1 on the of the oceans. So as I move this slider bar up, this is increasing amounts of carbon dioxide. It's about 400 right now. And so what happened to the pH value of the ocean? Well, you can see that this went from 8.1 down to 8.0. And so that is called acidification. When the pH goes down, it's still in the basic range because it's still above 7, but that's called acidification. So moving the slider bar as carbon dioxide increases, we're just going to have lower pH values. And let's look at this graph. No, let's not look at that graph. This will just lower our pH values as the carbon dioxide increases. And so that is going to be a problem. It better not get to this. So let's put it back down here, but that this will affect not just the pH values of the ocean. What's more important is the dissolving of the shells and dissolving of coral reefs that we really, this is one of those other things about humans affecting biodiversity. This is a huge one, and this will be the biodiversity of the whole ocean. Now, on the plus side, if we can get our act together and lower carbon dioxide concentrations, then we will solve the global warming, climate change, climate crisis problem, and also the ocean acidification problem. So I look forward to that day. And it is something that it is going to have to happen. And so that is your ocean acidification. We'll continue on. We're gonna look at a worksheet, but that I just wanted to show you the connection of pH to the carbon dioxide level, which is all invisible. We can't see any of this. And so there are skeptics around all of that, just that there were skeptics around carbon dioxide being linked to temperature changes. So there's chemistry behind it. There's a series of chemical reactions that leads to the lowering of pH because of carbon dioxide. And so the skepticism is because what does this stuff in the air that we can't see, how does that affect the coral reefs? And so there's the links are these chemical reactions on the worksheet that we'll look at. Okay, how do you guys feel about this? The chemistry of ocean acidification. This is still on the theme of modeling the unseen, because we can't see this stuff. We can't see what's going on in the ocean. We can't see these reactions, but we know they're going on. So this is the ocean. We know is basic. And this is actually already written here. So pH that is exactly 7, this is called neutral solution. That's only when you have exactly pure water. So that's water that doesn't have any extra hydrogens or any extra hydroxides. That's pretty rare. But pure water should be exactly equal to 7 because it has an exact equal concentration of hydrogen to hydroxide. This going back up to here, why is water a pH of 7? It's because this pH of 7, which is a neutral solution, has an exact equal concentration of hydrogen and hydroxide. They're both 10 to the minus 7. And that is a neutral solution and is only true of pure water. Okay, so going back down to this worksheet, the neutral solution of water means that there's nothing else in it. Well, when you're talking about a solution that's acidic, that means that there's more hydrogen ions. Or when you're talking about a solution that's basic, that means that there's more hydroxide ions. And so the ocean is slightly basic. Ocean water or seawater is slightly basic. It's about 8.2. So anything greater than 7 is considered basic. And so the ocean is basic. And that's oceans all over the world, okay? And so why is the ocean basic? It's because there's other stuff in the ocean. There's other compounds, and these are compounds. These 3 compounds are naturally present. So naturally is the key word. These 3 compounds are naturally present in the ocean. This was established as in the evolution of the planet that these compounds are in the ocean. Nobody put them there. It's not pollution. They are naturally evolved and have evolved so that the ocean, being slightly basic, can basically take up excess hydrogen ions. Okay, that's a system to basically absorb excess hydrogen ions, is that these 3 compounds are already present in the ocean. These 3 compounds are also present, as I mentioned in the video, in your blood. In your blood also has these 3 compounds: carbonate, bicarbonate, and carbonic acid, and it's the same system. It is so that your blood can take up excess hydrogen ions. And so they're naturally present in there. Nobody put them in your blood. They are naturally present in your blood, and your blood is also slightly basic. It's not 8.2, it's even more slightly basic. Blood is usually around 7.4. So remember, neutral is exactly 7, but blood is slightly more, and anything not exactly 7 counts as basic. So blood is about 7.4, 7.5, and that is so blood can take up any excess hydrogen ions. Okay, so the system can absorb, come on, let's try this. Come on, pen. I did something and it didn't like it. Okay, let me try it this way. No, sorry. Okay. closed it out and reopened it. So trying it this way, this is a buffer system. It's called a buffer system, basically to absorb any excess hydrogen ions, so H+. Okay, and so looking at the structures of carbonate ion. So we know carbonate ion, that's on the polyatomic ions list. And then bicarbonate, that's also on the polyatomic ions list. And you might have heard of sodium bicarbonate, that's baking soda. Carbonic acid, this is an acid. It's an ic acid with the name ending, and it comes from the carbonate ion. Now, these three compounds are naturally present in ocean water and in your blood, and they are not very different. They are very similar. You can see from the structures. This is the difference between carbonic acid and bicarbonate is one hydrogen ion. Basically, if you rip off this one hydrogen ion here, you'll get to bicarbonate ion. Or going the opposite direction, if you add one hydrogen ion, you'll end up with carbonic acid. Okay. From bicarbonate ion, from the middle structure, what's the difference between bicarbonate ion and on the left, the carbonate ion? This one hydrogen. So if you rip off this one hydrogen, you take it off, take this off, you'll lose one hydrogen and you'll end up with carbonate ion, which is CO3 -2 charge, no hydrogens. But you can also go the reverse direction and add that hydrogen right there, and you would end up with bicarbonate. So these three compounds are related. The only thing difference between them is hydrogen ions, okay? And so these compounds are naturally in the ocean and in your blood. This has been there for millions of years, and it maintains a slightly basic pH. So the concentrations of these compounds are set in the ocean. They're not changing. What's changing is the concentration of hydrogen ions. So humans, which is the effect is called anthropogenic. The anthropogenic effect of humans adding carbon dioxide to the atmosphere, well, that leads to an overall effect of hydrogen ions. And so it's through this series of reactions that we're going to follow as word equations. So each of these you'll see is a word equation that I'm going to write as a balanced equation. Okay, so this starts with the majority of that atmospheric carbon dioxide ends up dissolved in the ocean as aqueous carbon dioxide. So this is carbon dioxide, which is CO2. That's a gas. So that's G. And this ends up dissolved in the ocean. And this is CO2 when it's dissolved in the ocean is now aqueous. That's aqueous. So this is the what happens that you can't see this going on. You can't see the carbon dioxide in the atmosphere, and you definitely can't see it getting dissolved into the ocean. Okay, but it happens because water can dissolve so many things. Why does water dissolve so many things? Remember that going back to water makes those hydrogen bonds. Water is attracted to so many compounds. Okay, so this aqueous carbon dioxide, once it's dissolved in the ocean, will actually react with water in the ocean. So this is CO2 that is aqueous that reacts with the water in the ocean. So water in the ocean is H2O and it has the physical state L. Water is really one of the only compounds that has a physical state liquid. Even though aqueous solutions are liquids, we don't call them liquids because the AQ indicates there's something else in there. So this is reacting with water, and what you have is the product, which is carbonic acid, and we're given that chemical formula H2CO3. So carbonic acid, if you have your solubility rules handy, acids are always aqueous, and so we could add the AQ physical state there. This word equation is already balanced with the number of carbons on both sides, the number of oxygens on both sides adds up to 3, and the number of hydrogens on both sides is 2. So we know carbonic acid is unstable and it decomposes into hydrogen ions and bicarbonate ions. Carbonic acid is actually a weak acid. And remember, last time I talked about strong acids versus weak acids. And so this carbonic acid, H2CO3, that's aqueous, it doesn't sit around as H2CO3. It decomposes, and I'm going to put a double-headed arrow because it's a weak acid. It decomposes and some of it stays stuck together, some of it reforms. That's why it's a double-headed arrow. So there's a reverse reaction for a weak acid. Forward arrow is decomposing, and then the reverse arrow is reforming or not completely decomposing. So this decomposes into hydrogen ions. This is H+, and those hydrogen ions are still dissolved in the ocean, so they're still aqueous physical state. And then there's also the bicarbonate ion, which is HCO3. So that's HCO3 in parentheses, and that is also still dissolved. And so that's aqueous physical state. This is still balanced. Even though it has the plus and minus signs, you still have the equal number of hydrogen, carbon, and oxygen atoms on both sides. So these hydrogen ions are the added hydrogen ions. So this is what I was talking about, 26% more hydrogen ions in the oceans. And that's that problem of ocean acidification. Okay, this though gets to the part where what happens to all those extra hydrogen ions? Well, these extra hydrogen ions, they end up in the ocean because of this series of reactions that started with humans that added carbon dioxide, and these hydrogen ions get taken up by these compounds. And so these are compounds, the carbonate, the bicarbonate, and carbonic acid, they're naturally in the ocean, okay? So even though there's some relationship to the carbonic acid that I wrote here and bicarbonate, they're the same compounds, these are reactions that happen because of the carbon dioxide compared to the carbonate, bicarbonate, and carbonic acid that are already in the ocean that was established as an equilibrium system to take up hydrogen ion. So to show that this is differently, these hydrogen ions, I'm doing in red. So these hydrogen ions that we added, that humans added, leading to the problem of ocean acidification, these are still dissolved in the ocean and they react with carbonate ions, CO3 -2. And these are carbonate ions that are dissolved, so that gets a physical state AQ. And these will produce this bicarbonate ion. Okay, and so the problem is not the reaction, but where does this carbonate ion come from? And so this carbonate ion, this one, circling this in green, this carbonate ion from this reaction comes from calcium carbonate that originates from coral reefs and shells of marine life. Okay, and so these shells and the coral reefs have to dissolve to produce carbonate ion, which is that CO3 2-, this stuff that I circled in green. Okay, so, and they're not doing this with any like brain power or any like head honcho telling you have to dissolve. It is a system that is set up in equilibrium, that it's like a sponge, that it's, hey, there's extra hydrogen, then this is how the ocean has evolved to to basically adjust for extra hydrogen ion. But the ocean did not intend for humans to spend 200 years kicking out carbon dioxide into the atmosphere. So the net effect of all these reactions is that you have a lowered pH of the ocean to about 8.1 from the original 8.2. That's called ocean acidification, okay? But the other thing, and this is the bigger problem, is this reduced concentration of carbonate ion that's coming from coral reefs. Okay, so this is coral reefs have to dissolve, and this is coral reefs or shell that has calcium carbonate. You know, your bones also have calcium carbonate. And so, but we're not in the ocean. So these things that live in the ocean just start dissolving because this ion, lots more of this carbonate ion is needed. And that carbonate ion goes into this reaction and it is unintentional. Okay, so this carbonate ion, these shells are dissolving because that's part of the natural system, but it was not meant to accompany, or it was not meant, did not evolve for the amounts of carbon dioxide that humans have been putting out into the atmosphere. And so that's why I called it an anthropogenic effect. I remember I used this first in module 4. That's a human caused problem. That's what anthropogenic means. And so this is the upshot of it. And we can't see this going on, but there is, I mean, we can see it going on. Scientists are studying it, and there's proof of thinner shells, reduced coral diameters, and the coral bleaching effects. Now, to be really clear, coral bleaching effects are, as I mentioned, they happen 2015, 2016, just like drought. The ecosystem can recover after a bleaching effect. But the question is, how many times can the ecosystem recover? If it happens every single year, it's going to be impossible to recover at some point. Also, it's going to be impossible to recover as coral is dissolving itself. So it's dissolving. It's also hit with storms and higher ocean temperatures and the pH of the ocean. But ultimately, it's the dissolving of the coral that will be the biggest issue. Okay. So rain is naturally acidic, and this doesn't mean it's an acid. Okay. Acid rain is different. So you have rain that's close to pH 7. It is so water, natural water, is naturally pH 7. And so rain is pure water, and it should be pH 7 because pure water has an equal concentration of hydrogen to hydroxide. So remember that, going back up to here, is that when you have a pH of 7, the concentration of hydrogen ion is exactly equal to the concentration of hydroxide ion. That's called a neutral solution. And so that's the story with the ocean. Is it starts off water, but there's other stuff in there. So it's not only water. And because of that, it has a slightly basic pH because of other compounds in the water. So for rain and acid rain both start off as water and start off as a pH of 7 with an equal concentration of hydrogen to hydroxide. Well, then because of other compounds that are mixed in and dissolved in the rainwater, you get a slightly acidic pH. So it lowers the pH from 7 down. And that also is true of acid rain because of even more compounds dissolved in the rainwater that lowers the pH down from 7 even more. So let's take a look at the chemistry, the reactions of what's going on in rainwater and also in acid rain in this worksheet. So we start off with rain being just H2O. Okay, but we know that if you go measure the pH of rain, so we're going to do that in lab, it's actually less than 7. It's around 5 or 6. So rainwater is slightly acidic, slightly. Okay, it's not down to pH 1, 2, or 3, 5 or 6. But why is it? It's because of carbon dioxide in the atmosphere. And so carbon dioxide naturally in the atmosphere dissolves in the ocean. We saw that with ocean acidification. Carbon dioxide naturally in the atmosphere also dissolves in rainwater. So this is all happening up there in the atmosphere. So here's this word equation, carbon dioxide gas. We're going to turn into the chemical formula CO2 with the physical state G. Carbon dioxide gas from the atmosphere dissolves in rainwater. So when it dissolves, just like the ocean first step, that carbon dioxide dissolves and it becomes aqueous. It is no longer a gas in the atmosphere. Now it is dissolved, which means it is AQ, aqueous. So once that carbon dioxide is part of the rainwater, that aqueous carbon dioxide will react with the rainwater. So it reacts with the water in the rain. So this is water, which is H2O, and it has the physical state L. This produces carbonic acid. So either from the name that it is an ic acid, that is the carbonate ion, or from the previous worksheet, we know that carbonic acid is the chemical formula H2CO3. And acids always are aqueous physical states. So I'm going to add an AQ. So we know that carbonic acid is a weak acid. It was a weak acid before, it's still a weak acid. And what happens with weak acids is they partially ionized. That means it breaks apart into the ions with the reverse reaction. So you need to use the reverse reaction arrow, because that's what a weak acid does, is it breaks apart into the ions, but not well. So there's some reverse reaction to reform, or that not all of them broke up in the first place. So let's take that carbonic acid, which is H2CO3, AQ, and this breaks apart into the ions, which are H plus, that's the hydrogen ion, and then HCO3 minus, that's the bicarbonate ion. And this could also continue on and also break up into another hydrogen ion and the carbonate ion. That's CO3 minus 2. Okay. But what you end up with, what's important is this. These are hydrogen ions that are in the rainwater and they weren't there before. It starts off with carbon dioxide gas. And because of the series of reactions, you end up with additional hydrogen ions in water. Okay. And so these are additional hydrogen ions. And when you have more hydrogen ions, that means lower pH. That's a lower pH value. And that pH goes from what started off as 7 down to a pH 5 or 6. Okay. And so that's why you can take samples of rain and measure those samples of rain. That's what this is in the US. You can measure those samples of rain and see that here in LA, you'll have a pH 5.4, 5.6. Colorado 5.1. You can measure samples of rain and it'll be a pH of 5 or 6. But here, these measured samples of rain, as you look on the East Coast over here, get to the orange. So what is the orange? The orange values are pH 4.5. So when you have a pH of less than 5, you're talking about acid rain. Okay, so even though rain is a pH of 5 or 6, which is the acidic rain, that is natural. Having anything lower than 5 is considered unnatural acidity. Okay, so let's take a look at what goes on there. Is that we have rain is naturally acidic. It's a pH of 5 or 6. Well, what happens when you have, and that's because of carbon dioxide gas in the atmosphere. That's naturally there, okay? But when you have other things in the atmosphere, like air pollutants, that leads to even lower pH values, and that leads to a lower pH and acid rain, okay? So let's take a look at that. When you have this area that has not only carbon dioxide gas, but the pH of the rainwater in Ohio. So here's this question, what's the pH of the rainwater in Ohio? So here's the state of Ohio. And you can see that it's around 4.7, 4.4. So it's between 4.4 to 4.7 is the pH values. And that's considered less than 5 is acid rain. Okay, so when the pH is less than 5. And why is it? Because of air pollutants that are sulfur dioxides, those are called SOx, and nitrogen oxides, those are called NOx, okay? So sulfur dioxide comes from coal-fired power plants. When you burn coal, it has small amounts of sulfur, and also small amounts of nitrogen, but those little amounts of sulfur will lead to carbon dioxide gas emitted when coal is burned. You also have nitrogen dioxide that comes from engine exhaust. And this is when gasoline combustion engines are hot. The hot combustion engine results in side reactions happening. And the main side reaction to produce nitrogen dioxide, or NOx, is when nitrogen from the atmosphere reacts with oxygen from the atmosphere, just because there's a hot spot, which is the engine. Okay, so when you have this reaction, the word equation says sulfur trioxide gas. So sulfur trioxide is SO3, and that's a gas. So I'm going to put a G physical state. When this dissolves in rainwater, okay, so sulfur trioxide gas from the atmosphere dissolves in rainwater, it produces SO3. It's aqueous, just like carbon dioxide dissolves and becomes aqueous. So this is an example of SOx, which is SO2, sulfur dioxide, or SO3. Basically, the X stands for how many oxygens there are. And both of these come from coal-fired power plants. Okay, so that aqueous sulfur trioxide, once it's dissolved in the rainwater, okay, so that is already there, it will react with the water. So it will react with H2O, and that's a liquid, and the product is sulfuric acid. So from the name sulfuric acid, the name ending is ic acid. That means that the anion is sulfate. And so this is the chemical formula of the sulfate anion, SO4 minus 2 with the hydrogen gives you H2SO4. That's the chemical formula for sulfuric acid. Because it's an acid, I can put the AQ physical state. So sulfuric acid is a strong acid. And as we saw in the last lecture, what happens to strong acids, they are completely ionized. So compared to weak acids, there is no reverse reaction arrow. So completely ionized means that you have the chemical formula of the acid, which is H2SO4, and you only have a forward arrow. You're probably more used to only the forward arrow. Those are the ones that I usually draw for chemical reactions. So you have only a forward arrow, no reverse, there's no backwards. And that means this breaks up into the ions, which are 2 of the hydrogen ions. Okay, that's coming from that 2 subscript. And there's also the sulfate SO4, which is the -2 ion. Okay, and so what this means is that there's hydrogen ions. These are added hydrogen ions added to the ones that were already there because of the carbon dioxide. So the pH of rainwater was already 5.6, 5 or 6, and now it's going to be even less than 5, because when you have even more hydrogen ions, that means an even lower pH. And that's a pH of even less than 5. And so that is your acid rain. Okay. Let me remember to record this. Why is it that over here in Ohio, there's acid rain, and over here in LA, there's not? Well, remember, going back to this is because this is where you have those air pollutants, which are the sulfur dioxide coming from coal-fired power plants. So those coal-fired power plants, those are factories in Pennsylvania and Ohio. You remember Pennsylvania had air pollution because of steel. There's a lot of steel factories that burn coal in order to manufacture steel. And so the manufacturing of steel, this is the state of Pennsylvania shown here. That manufacturing of steel, which is why you have the football team, the Pittsburgh Steelers, maybe? The Steelers are from the state of Pennsylvania, and that's the steel processing, the steel factories. They're burning a lot of coal there, and they're producing a lot of sulfur dioxide. So there's more air pollutants, and that leads to not just air pollution, but also acid rain. Okay, so let's take a look.